pen puzzles. Okay. So the way that these work is you see that there are 6 just darling little pigs in pen A. And the idea is to try and figure out how many pigs are in pen B and pen C, knowing that these numbers here on the bridges represent the total amount of pigs between the 2 pens that they connect. Okay? Let that sink in for a second. All right, so this one's not too bad. Who can tell us how many pigs are in pen B? Yeah. 5, right. Okay. 5 because we have 6 in the other. That's what would make 11. And that leaves how many pigs for pen C? 4. Okay. So we're going to take away the pigs from pen A and now ask you to figure out how many pigs are in pen A, B, C. You can use scratch paper if you want, but it's not necessary. When you think you know, raise your hand and we'll check and see if you're right. Yes?
So there's 2. Is 8 in pen B, 2 in pen A, and 3 in pen C.
Are you guys on board with her solution? Does 8 and 2 make 10? 8 and 3, 11. 3 and 2, 5. This fits. It works, right? All right, one more. She knows again. She's just giving you guys a chance. Yes. All right, does that work for everyone? Okay. What strategies were you guys using? Even if you weren't the first one that figured it out, you were sitting there doing something to try and narrow down the possibilities, right? What strategies were we using to determine that these must be the values here? Yeah. Guess and check. Good. How many of us were doing guess and check? Okay. In these problems, guess and check is a completely valid way to do them. Okay, what makes guess and check a really good strategy for these problems? What is it about these problems that's like, oh, I can just guess? Yes. Okay, so you can plug in the values to see which ones work. And what about what was in the problem makes that easy to do? Because I could change a couple things up here and that wouldn't be so easy to do. Yeah. Yeah, that you actually know some values, right? And those numbers, were they super large? No, they were pretty small, right? So like if I changed these to thousands or hundreds of pigs, would guess and check become more difficult? Yes, okay. There also is something else about this problem that's making it a little simpler. Yeah, that we're dealing with whole, I mean, I guess, I don't really know, but it seems as though it needs to be a whole number, right? And given that it needs to be a whole number, that makes our guesses a lot easier. If this wasn't about pigs and it was about how much money was in each thing, and all of a sudden you can have these different decimal values, your inclination to be guessing would probably lower a little bit when you bring in numbers like that. Okay? And what you guys were really doing here, I'm going to write up a couple of mathematical things. Oh, maybe not. So would you guys agree that when you look at this problem, these 3 equations would explain or define the relationships that you're seeing there? Okay. But if I gave you guys this problem instead of this picture and introduced it a different way, would you have probably used guess and check? No. Right? There's not pigs here, so you don't know there's for sure whole numbers. And because I wrote algebra, you would probably immediately start doing some algebraic things, right? When you look at the handout that I gave you, they are basically systems like this, but they are a lot more complicated, right? So guessing is not really going to be the approach that we're going to use. It might work some of the times, and actually the handout I gave you has an answer column, and it's on purpose. I mean, you could technically just go through all the answers and eliminate, but you won't get good at the skill that you need to master. what are our options to solve something like this? Okay. What type of algebra have you done before that can help you take sets of equations like this and do something with them?
Substitution.
Good. So substitution is one way. Elimination is another way. Have you guys done anything else to solve systems? Graphing, yeah. So graphing is actually a super cool way to look at it, because the cool part about graphing is it gives you context. Like when you guys are solving a system of two equations and you graph them, the solution is the point that they meet at, right? That's an important conceptual understanding instead of just being like, I am a computer that will find you X and Y. It's like to understand what those X and Y values mean and how they're related to each other, okay? But we don't like graphing all the time, because if we graph it and it doesn't end up on a very particular spot on our graph paper, it could be very difficult to give someone the exact solution, right? So we are going to rely heavily on substitution and elimination, okay? What else is more complicated about what we have here than what we were doing previously in Algebra 1? Yeah, there's 3 unknowns. In Algebra 1, you always dealt with 2 unknowns, okay? And with those 2 unknowns, you needed 2 relationships to figure it out. Here we had 3 unknowns, and we needed all 3 relationships to figure out certain things, right? If one of these was missing, we wouldn't be certain about the relationship. So now that we have 3 unknowns, we need 3 equations, and that's going to complicate our substitution and elimination just a little bit, okay? And then to give you guys some conceptual understanding, I said this was important right here, right? That knowing when you're solving a system of 2 equations, that's the place where the lines cross. What does that mean about 3? So there actually exists 3-dimensional graphing in mathematics. We are not going to do it. It's very difficult actually to draw a 3-dimensional graph on a 2-dimensional piece of paper. But just to give you a very small, very, very, very small idea of how it works. Let's say that I'm looking at the tiles here. I'm standing right here and it's like the origin of like an XY axis along my floor. Okay? So like I'll do it from your perspective. So like moving that way is like positive X values, right? And this is our negative X. And then there's like positive Y values and negative Y. Okay? So if you guys graphed the point 3, -2, my pen, if I was plotting it at that point, would go over 3, down 2, and it would lay on the floor on that coordinate plane, marking that point. Fair enough for everybody? When you add a 3rd dimension into graphing, and let's say I add a 5, you just added a z-axis into the graph. So you still have your x and your y, but now, like where I am physically standing, I am like the z-axis. And let's say the positive z is this way, going up towards the ceiling, and the negative z would go down through the floor. Does that make sense to everybody? Add the 3rd dimension. I can plot 3, -2, 5. I now still go to 3, -2, but then instead of laying here on the floor, my pen goes up 5 spaces and floats here in 3-dimensional space. Is that okay with everybody? Just a very small, we aren't going to graph it, we aren't going to look at a bunch of 3-dimensional things, but just so you understand, like it exists, it's out there, some people study this, those kinds of things, okay? But we are going to solve 3 equations with 3 unknowns in them and write the answer like an ordered triplet, not an ordered pair. And I just wanted you to know that that could exist. It could be a point in 3-dimensional space, okay? All right, so now we're going to look at how to do this. We're going to do one example on here, and then I think you guys will actually have time to work, which is something we don't always get in here, so that would be nice. So instead of graphing, because you can see that 3-dimensional graphing can get a little difficult, and these aren't points, these are like not just lines in 3-dimensional space. Because they're 3-dimensional, they end up being like planes. I don't know, it's a little crazy, okay, about how they'll connect. So we're gonna rule out the graphing option as how we're gonna solve it. We're just gonna understand that point could be a point in 3-dimensional space. And so we're gonna try and rely on substitution or elimination to help us get through a problem that's just bigger than the problem in algebra. So I'm not going to teach you a new strategy. All I'm going to say is you know a strategy that you could apply to a more difficult situation, and our job is going to be just to kind of sort through what it looks like when we apply it to the more difficult situation so you're more comfortable with it, okay? So are you guys okay if we approach it with elimination instead of substitution? Is that okay with everyone? You can do substitution, but can you see in this case how it could be a little tedious because there's multiple variables with multiple coefficients, okay? So I tend to like elimination better, but that doesn't mean that you can't do it with substitution. I'm going to number the equations 1, 2, and 3 simply so that when we're sitting here in class right now talking about it, we're able to communicate which equation we're talking about. We don't have to be like that one, okay? We'll talk about like equation 1, equation 2, or equation 3. So we're going to try and do elimination. We have 3 equations in front of us. Does anybody see a place where they feel like they could start? Okay. So she's saying number 1 and number 3 have something kind of already laid out for us. They have a negative 3z and a positive 3z. So if I combine those together, the z's will cancel out. That seems like a good place to start. Do you have to start there? No, we're going to do that together because we made that choice as a class. That seems like a logical thing to do, but that doesn't have to be the decision. Okay, so I'm going to keep track of my work kind of like this. So if you don't need to keep track of this, then you don't need to keep track of this. But if you're going to look back at your notes and not understand what we did, then you need to make some notation like add equations 1 and 3 or something like that so you know how we got through this problem. So I'm going to recopy them. You guys are going to make sure I don't make a mistake because every time you copy something and are doing the work on your paper, you are going to look up and make sure that it matches with mine because sometimes, I'm not going to lie, my adding and subtracting or multiplying isn't always on point. So you guys will be able to correct that. So that's what we're doing there, and we're getting these 3 z's to cancel. And so we would get something like 8x plus 10y equals negative 38. Okay? So we accomplished something. We got rid of z. However, it's not the same feeling you have in Algebra 1. In Algebra 1, when you cancel out the y and all you had was an x and y, like you have x, right? You figure out the exact x value. And we're not there. But notice what we do have. We have something that looks like it belongs in an Algebra 1 problem. Fair enough? Like it got smaller. That's good. That's progress. But now we need another one of those. We need to make an Algebra 1 problem basically from our more complicated Algebra 2 problem. So we're trying to take our 3 equations and 3 unknowns, and our first step here is to try and rewrite it as a system with 2 equations and 2 unknowns so we can just do what we did in Algebra 1. Okay, that's our goal. Suggestion?
I see a way to get rid of y. Just multiply the same equation by 2 and then substitute.
Yeah, you can do that too. All right. So if we are, yeah, Luke, no, go for it.
Sure, I was going to say, did you ask like what we could do next?
Yeah.
So we can multiply the second equation by 3.
Okay.
And then do it between 1 and 2.
And combine it with 1, you said?
Yes.
Okay. All right, so he's saying take the second equation, multiply it by 3. Sorry, move my screen a little bit. And then add 1 to it. That will work. And then we were also given a suggestion about doing substitution. And again, that's not incorrect, okay? You can do substitution at any point that you find it feasible. In my experience, that's going to be a little different for everyone in here. So we kind of start like this, and then the people that see substitution can definitely go through and do substitution. So I'm going to multiply the whole second equation by 3 and make sure that I don't mess it up. And then I'm going to add it with the first equation. So this was a really good move. Not only did we cancel something out, but that something that we canceled out, more specifically, was a z. And the reason why it's so important at this point that we canceled out a z is because we already made one move, right? We already canceled out a z previously and made an equation with x and y. If I want to do this like an Algebra 1 problem, I need another equation, and it specifically needs to have x and y. I don't want x and z or y and z. I can't finish that problem. I'm going to have to keep doing a lot of things, okay? Instead, I want just x's and y's. So the numbers aren't that nice here, but we have 27x minus 13y equals 199. Okay, and that's my second equation to build my algebra 1 system, basically. Okay, and now I'm just going through what I would go through in algebra 1. In other words, I have to repeat this substitution elimination process yet again. Okay. So what do you guys want to cancel from these two equations? We're basically starting over. We made a smaller system of equations, and now with this smaller system of equations, we want to use substitution or elimination again. Okay. So what variable do you guys want to try and cancel out? I have an opinion. I know the numbers are ugly, but I personally want to use y, because at least in one of the equations I get to multiply by 10, and 10 is easy to multiply by. Okay, so since none of you spoke up very quickly, I'm going to go with that. And then I'm going to multiply everything in this other equation by 13. Okay, to give me a new system where hopefully those y values cancel out. Okay. And sometimes we do make you guys multiply together numbers. I'm not going to make you multiply together 38 and 13. If you got here, I have faith that you can do double-digit multiplication. So let's see. 494. All right, and then 270x minus 130y equals 1,990. Did I mess up? Oh, negative, thank you. You'll see why that's very important in a little bit too. Good job. Okay, yeah, my copying errors, and like it's a negative 494. I'll change it right now. Okay. All right, so the y's will cancel out. Do my other numbers look okay? You guys did it? Did we get the same things? Yes? Okay, so we're getting 374x equals, I'm totally going to be lazy right now, 1,496. And now we can finally figure out x. And x is equal to 4. Huh. Turned out pretty nice for having such ugly numbers. Okay. So x is 4. Am I finished with this problem? How much of the problem am I finished with? A third. I've found a third of my solution, okay? This, right? The answer to this problem is an ordered triplet like we talked about, where x is the first variable. Every time they give you the letters, I know for x, y, z that makes sense to us. If they give you like r, s, t, just put them in alphabetical order when you write the ordered solution, okay? That's kind of the order they go in. So x is 4. How are we going to find the other solutions? Yeah.
I would plug x equals 4 into 8x plus 10y equals -3.
Good. So just like in Algebra 1, once you get one solution, you're plugging in to find the others. But here's the thing. Don't take the x and plug it back into the very first equations, because then you still have systems, right? Because they still have y's and z's in them. I can plug them into any equation that I made from the original equations. So I like his choice of 8x plus 10y equals -38, because if I plug the 4 in there, I will be able to find the exact value of y. Okay, so I'm going to go ahead and do that. I'm going to plug in the 4. You guys are going to do the same thing, and at the end, look up and make sure that my arithmetic matched yours. 10y, -70. So you finish it, but it looks like y should equal -7. So I have a couple confirmations out there that that makes sense. Okay. Now I have 2/3 of my solution, and that second third didn't take nearly as long as the first third, thank goodness, right? All right, how am I going to get the third and final part of my solution? Perfect. I'm going to plug x and y into one of the first equations where I can then go ahead and find z, okay? So you can choose whichever one you want. I'm going to choose this 7x minus 5y plus z equals 72. Okay. I don't know. I just liked that Z didn't have a coefficient. 63. So Z is equal to 9. All right. So 4, -7, 9 is my solution. And remember what that means. It could be a point that these things are meeting in 3-dimensional space. It also means that an x value of 4, a y value of -7, and a z value of 9 make all of the equations in your system true. Okay, so if you wanted to check your answer, how would you go about doing that? What's that? You could make a graph. It would be really hard in this case with the 3Ds, right? I'm really not good at it. That's why I giggle when I say it. I've tried to do it before. I mean, I had to do it in college for one of my math classes, and my graphs just don't look that great. And they're extra hard to read the point off of because you have to draw it like at a slant on the 2-dimensional paper to try and make it look 3-dimensional. Yeah, so I would advise, unless you have a program that can graph them for you and make sure that's the case, that for us, if we're doing it pencil paper, that we plug it in, okay? And should it just work in one of them? No, it should work in all 3 of them, okay? Is that all right with everybody? All right, so that's the general idea. Did I teach you anything new as far as mathematical processes? No, but we took something that you already know and we applied it to a much more complicated situation. Technically now, if I gave you a system of 10 equations and 10 unknowns, that's how you should feel when I say that, right? You would be able to solve it, but you'd be crying and cursing me along the way, right? Because it would just be this over and over and over and over to try and narrow down these equations to things that you could actually make some progress on, okay? So take a look at your homework, which is the other side of that handout. When you look at the systems, they generally look like what we just did, right? But there's a couple on there that could cause you a little bit of kind of indecision about if they can be approached the same way or not. When you guys look at the problems on there, which ones stand out as looking different than the rest? Yeah, 5 looks much different, right? So I just want to, I guess, kind of build confidence for you at the beginning. You actually do totally know how to do this using the same strategy that we just did, right? When you look at 5, do you see anything that you could combine together and eliminate? And remember, you can multiply stuff by something if you have to. So somebody raise your hand and give me an example of one way we could approach number 5 and eliminate something.
The first and third equation. Oh, wait, no.
Okay, that's so funny. This totally happened in last class too, with the person sitting right there. And it's totally a good example of what he's looking at. He goes, oh, the first and third, never mind. Because he sees the 2 and -2, that's exactly what our eyes should be looking for. But then we should recognize, just as he did, we can't actually combine those together because the 2 is a coefficient on y and the -2 is a coefficient on z. That's not going to work, right? So could we multiply the first equation by 2 and then combine the first and second equation together to eliminate x? Yes. And then let's decide if that's actually good or not. If you took the first 2 equations, combined them together, and eliminated x, you would have a new equation with what variables in it? Y and z. That was perfect, right? Because what does your third equation have in it? Y and z. You don't even have to go make the other equation with y and z in it because it's already right there. So it might look slightly different, like you might not have the exact same 6 steps that we went through, but the same strategy can get you to the same place with all of these problems. Is that okay with everyone? So you're going to have some class time to work. I would recommend that you don't necessarily start with the simplest problem, but if you see something on there that seems like it's going to be more difficult, I would actually skip to that problem because this is the room where you have all the people that can help you, okay? So the remainder of the time, we're going to work on trying to get some of our homework done so you guys don't have as much tonight.